in first thing is always chemical shift, okay? Because the chemical shift value of a proton is directly associated with its local environment, or the most reliable information you get is the proton chemical shift value is usually directly associated with the electron density around that proton. Why? Because the proton you are dealing with, they are not isolated protons. They always have electrons around it. And those, if you have electrons around the proton, those electrons will circulate under the influence of the magnetic field, if you're going to put it in the instrument. And such a circulation will create a magnetic field against the external one, like we have shown here. If this is a magnetic field, okay, instrument field, circulation of electrons will create a field against, okay, against, the external field. So if that means the electrons around the proton will shield the proton. So the higher, this shielding, okay, will reduce the field, okay, magnetic field experienced by the proton, reduce the field. And if the field, magnetic field strength is weaker, its resonance frequency will become what? The field is weaker, the resonance frequency, or alpha. If the field is weaker, the resonance frequency will what direction? The field is weaker, the energy difference between the two states will be smaller, and the resonance frequency will be decreased. Okay? So that's always the high electron density, low resonance frequency. And the resonance frequency is directly parallel to the chemical shift. So low resonance frequency, low chemical shift value. So that means that if something has a low electron density, you're going to see high chemical shift value. So this is always correlated. Okay. So now, in addition to chemical shift value, you also need to look at the number of signals. This basically tell you how many types of protons you have in the compound. And the area on each signal tells us how many protons, that signal corresponds to. Like, look at this example. Here we have two peaks, two signals. Tell us there are two kinds of protons. And obviously one is CH3 proton, kind 1, kind 2 is CH2 protons. And the area on each peak is reflected by the height, the step height at the S curve. So the area on each peak is basically the red one is 50% bigger than the blue one, because there are 3 red protons and only 2 blue protons. Okay, so this area on each peak directly proportional to the number of protons. Okay, then look at the chemical shift value. Why red protons is only like 3.4 ppm, and the blue proton is 4 point something proton, okay, 4 point something ppm, because the red proton, okay, is only on the direct influence of electron withdrawing group, inductive effect, because here you don't have, all the group atoms here, we are looking at is, all the protons are connected to sp3 hybridized carbons. So you don't really need to consider the, the resonance effect. So that in this particular case, that you only consider inductive effect, that oxygen is the electron withdrawing group when you consider inductive effect. So these 3 red protons, they are under direct influence of the electron withdrawing oxygen atom. And then the blue protons, if you look at it, not only it's under direct influence of the electron withdrawing oxygen atom, also it's under direct influence of the CN triple bond. CN triple bond also electron withdrawing group. That's why the blue protons has a substantially higher chemical shift value, 4 point something, compared to the red protons. And now, in addition to the chemical shift value, number of peaks, area on each peak, we also, if you are able to zoom in at individual peaks, you will be able to find that some of the signals they actually split into multiple lines. Okay? And the number of lines, in a particular signal, okay, is called a multiplicity. Okay? So if it's a signal only has one line, the multiplicity obviously is 1. Okay? If a signal has 2 lines, for doublet, the 3 lines for triplet, 4 lines for pent, and 5 lines, pentlet. Okay? That's just the name. Okay? So in the simple case, multiplicity is equal to n plus 1. What does that mean? Okay, means that this n is a number of equivalent vicinal protons. Like in this one as example, okay, if you are looking at the signal of this blue proton, okay, you just count. If you want to know how many lines this blue proton signal will be, just count the number of its vicinal protons. What means vicinal protons? This blue proton connect to this carbon, okay? You count the number of protons connect to the neighboring carbon atoms. So blue protons connect to this carbon, okay? Its neighboring carbon obviously is this carbon, okay? And you have how many protons connect to here? You have 3, okay? So the signal of this blue proton will split into 3 plus 1, 4 lines, okay? So that's how you're gonna know the multiplicity. But let's look at the proton atom mass spectrum of this compound without checking the multiplicity first. So first thing is, if you look at this compound, how many signals you are expecting? How many signals? How many types protons do you have? Look at this compound. How many types of protons do you have here? Just look at how many types. We have 4 protons, but how many types of protons? 2. Well, that's pretty straightforward because one is the methyl proton. The other one is the type is the methyl proton. Methyl proton, you have 3 of them, but all of them are equivalent. How do you know they're equivalent to each other? Do the replacement test. So if you replace, let's say, if you replace say if we here we can make a copy of this guy. So if you are you are wondering whether this proton and this proton they are the same type, so you can try to do the replacement test. Say, let's do this. Okay, so if we replace this proton, okay, with a group you don't already have, say, let's say put the fluorine here, you get a compound 1, okay, and then for this proton, you also can replace with say fluorine. And if you try to name those 2 compounds, so-called 2 compounds, okay, they're actually the same compound, okay. So that can prove that all the protons all the methyl protons, they are equivalent. Okay, you only have two types of protons, so expecting two signals here. Okay, and then what about the chemical shift value of these two signals? How do we judge that? So basically, you're considering inductive effect. And if you consider inductive effect, the two electron withdrawing group should catch your eye is these two chlorine atoms. Okay, and if you look at these two chlorine atoms, obviously the blue protons, okay, they are under the strongest influence of these two electron withdrawing chlorine atoms. So that's why the blue proton, the single one, has extremely high chemical shift value. It's nearly 6 ppm. Okay. Now if you look at the methyl protons, okay, they obviously are at least one more bond away. One more bond, basically the one chemical bond further away from the two chlorine atoms. So the inductive effect on those methyl protons, they are appreciably weaker. Okay, I'm not saying it's very weak, but it's appreciably weaker. Okay, so now it's only about 2 ppm. A typical methyl proton, I hope you can somewhat remember a typical methyl proton is about 0.9 ppm if without those inductive effects. So you see these two chlorine atoms still have a sizable effect on the chemical shift value of those methyl protons. So, increase from 0.9 to about 2.1, okay? But it's still much weaker than this because of the inductive effect. It attenuates, weakens very quickly over the distance. So one chemical bond away, inductive effect is huge difference. You can see here. The somewhat quantity will tell you one bond away, this proton, blue one and the red one bond away, inductive effect is huge difference. Okay, from 6 ppm to about 2 ppm. It's a very large difference. Okay, and this is a qualitative chemistry. I'm not asking you to memorize it, but you should know that the blue peak should have much higher chemistry value than the red one. I'm not asking you exactly how much, but obviously higher. Then next thing is about the area of each peak, because you only got one blue proton and the 3 red or pink, whatever color protons. So the area, if you look at area ratio between the blue one and the red one should be 1/3. Okay, so if this is a 1, this is going to be 3. Okay, so if you're using a ruler to measure this step height, okay, will be 1/3 of this step height. I will show you how to do this kind of thing if you need to do the homework. Okay, so you always do like the basically draw the linear extrapolation for linear part of the extrapolation, and draw the linear extrapolation part. Then you're using a ruler to measure this height, this step length. Okay, same thing here. Draw the linear extrapolation. And draw the linear extrapolation here. They are using a ruler to measure. Okay, you look at this length ratio that tell you the area ratio. So you probably can see obviously the red one, the height more than twice of the blue one. It's actually, if you use ruler, it's actually 3 times. Okay? So this is just the information we have learned so far is not involving multiplicity yet. Basically, chemical shift value, the number of peaks, and the area. Those 3 type of information, they are extremely reliable, never have an issue. Okay? Multiplicity sometimes could be complicated. Okay? Sometimes, okay? But we will see. Okay? So now, if you zoom in the peaks around 2.1, you will see actually it's double it. Okay? And if you zoom in peak at around 6, is actually quartet. Okay, why that's the case? Why this red peak is double it here? Okay, because those the 3 methyl protons, okay? If you want to know the multiplicity, just check the number of equivalent protons. They are vicinal to the protons give you this signal. So the red protons give you the peak at 2.1 ppm. So it's vicinal protons. They are basically only one, blue one, okay? So apply n+1 rule, the signal will split into the doublet, okay? And similarly, if you look at the blue proton signal, we know it's around 6 ppm. So if you want to know how many lines this signal should split into, just check the number of vicinal protons. So this is a blue proton carbon, okay? And this carbon is its vicinal carbon, okay? And the protons on this carbon is vicinal protons. So you have how many? 3 of them. 3 plus 1 is 4. So that's how the multiplicity comes out. Now, you may ask, why the signal of the methyl proton was splitting into doublet, okay? That is because if you look at the 3 methyl protons, obviously you experience the magnetic field B0, okay? Also the shielding effect of electrons. But on top of that, you know, those blue protons, okay? The blue proton, they, you know, each blue proton has a nucleus there, proton nucleus, right? The blue proton, it's just like all nuclei, they are spinning. The blue proton, as far as magnetic field is concerned, you can treat the blue proton as a small magnet because the blue proton is spinning, okay? And a small magnet, and if you put in magnetic field, this small magnet, okay, could have 2 arrangements. Either will be aligned together with external field, a small magnet, spinning blue proton, or anti-parallel to the instrument magnetic field, okay? Now, only these 2 possibilities. Now, if you consider this particular case, if we consider the small magnets, this one has a magnetic field, let's say we call it BH, okay? This BH is obviously much weaker than B0, okay? So for this, so the probability of the small magnets are parallel and the anti-parallel, they are pretty much 50-50%, okay? Pretty much 50-50%. Well, to be exact, this one should have a bit higher probability, okay? Maybe let's say 51%. So this one should have a bit higher probability than this one, because these guys, you know, this small magnet that's created by spinning proton, when it's parallel to the external field, will be slightly more stable than anti-parallel. But it's pretty close, say 51%, 49%. That's probably more like the case, okay? Let's say 51, 49. 51, okay, 49. A bit more, okay? So now, this small magnet is also gonna influencing the magnetic field experienced by those 3 red protons. So if you think about what kind of field those 3 red protons they are experiencing, forget about the shielding effect for the time being. We just think about before the shielding effect of electrons applied. So for if you consider magnetic field experienced by those 3, you know, the red protons, in this case, the field experiences B0 plus BH, because this field is parallel to external field. So so these 3 red protons, in addition to feeling B0, it also feels this BH, okay? And obviously, in the right side case, the field experienced by the red one is B0 minus BH. That's why you see 2 lines, because of the impact of the vicinal proton, okay, will modify the magnetic field experienced by the red proton. So this modification could be enhancing or slightly decreasing the field. Okay, this field is this effect is very weak but detectable by instrument. So it shows as a splitting of the signal. Okay? So if only one, there's either parallel or anti-parallel. So you see only two lines. If a particular proton, okay, only has one vicinal proton, so that vicinal proton will split the signal of this proton into double. Okay. Now, if you look at the blue proton, basically let me put the molecule here. Discard. Let me put the. So if you look at the blue proton, right, signal of the blue proton. So in addition to BZ, the blue proton also gonna experiencing the magnetic effect of those three red protons, and each the red proton, because they are spinning, each will behave like a small magnet, and those small magnets, once put in the external field, instrument field, the small magnet could either be parallel to the external field or anti-parallel to external field. So we assume that the external field is going up. Okay, so then if we consider how the magnetic experience of the blue proton is basically you will experience the B0 and also going to experience the the magnetic effect of those three red protons or pink protons. What's the color? Is it pink or red or purple? What do you call this color? Pink. Okay, it's fine. But anyway, so let's say in addition to the B0, the blue proton also going to feel the impact of magnetic field of the pink proton. But you have three of them, and these three of them, each one could either be parallel, be anti-parallel with the magnetic field. Okay, so if you count all the possible combinations, you will see only one combination, all the three protons will be parallel to the external field, and only one combination will be all the three small magnets that created by spinning red or pink protons, okay, will be anti-parallel to the external field. There's only one combination. And there will be three combinations where the two of them will be parallel, okay, and one of them gonna be anti-parallel. And also they're gonna be three combination of two of them anti-parallel and one of them gonna be parallel. So two of them anti-parallel, one parallel, two of them anti-parallel, one is parallel. Okay. So if you look at the net, the net magnetic effect of those kind of combinations, you will see that in this particular case, the net effect of the three pink protons is basically each of them gonna be parallel to the magnetic field, will contribute the BH. Three of them will be plus 3 BH, right? And this one will be, because each of them is against the opposite external field, will be minus BH. Three of them are going to be minus 3 BH. And if you do a little math, you will see these three combinations, all of them going to have plus BH, and these three combinations, all of them going to minus 3 BH. Each of them going to be minus BH. So overall, you will see four different, strengths of magnetic field experienced by blue proton. That's corresponding to 4 lines. Okay, and the intensity of those 4 lines is 1331. Okay, and I'm not gonna go after the details of those those ratios. Okay, and if you, for those of you interested in those ratios, the intensity of the different lines in multiplet means doublet, triplet, quartet. They follow basically can be described by Pascal's triangle. You guys know what's a Pascal triangle, right? The polynomial coefficients. Anyway, if you don't recall, it's fine. I'm not gonna test it, but just if you're interested, the intensity follows can be described by Pascal triangle. Okay? But anyway, so the spacing between couplets, those lines called coupling constant. And because this, if you look at the space between those lines, actually always is 2BH. This is on plus 3, plus 1, right? And in the previous case, doublet plus BH to minus BH. So all the spacing between labeling line always 2BH. And then this has nothing to do with instrument magnetic field, because this is just they describe the magnetic interaction between a pair of the nuclei. So it has nothing to do with the instrument magnetic field. And the protons that couple each other display the same coupling constant in both signals. So, like in in this case, if you measuring because of the blue proton and red protons, okay, they are influence each other, right? So if you're measuring the line between these two, the spacing between these 2 lines, say this line and this line, I should have shown between this line and this line and this line and this line, okay, and this line and this line, they're all the same, okay, and this spacing also is equal to the spacing between this line and this line. Okay. All right, so now let's look at hopefully you have some basic understanding of how the spin splitting work. So the spin splitting pattern, just how many lines the signal split into, tells us basically how many vicinal protons we have for a given signal. So let's look at just go through a few examples. Okay, look at the proton NMR spectrum of this compound, ethyl bromide. Okay. So first, for this compound, how many peaks, how many signals you are expecting? Matt, can you tell me how many peaks you expect from this compound? How many signals, how many peaks you are expecting from this compound? Okay. Then, Robert, how many signals expected from this compound? Huh? 8? No, I'm saying how many peaks? How many signals? 2. Yes. Hey, 2. That's how many, because it's 2 kinds of protons. Okay. It should be very obvious for this compound. Okay. This is very simple compound. If you don't get this one, I'm going to be very worried for the coming exam. Okay. 2 signals. Okay. And the chemical shift value of this one should be substantially higher than this because of the bromine reaction with join group. Okay. It's a bit, the bromine obviously has the strongest impact to the CH2, much stronger than the CH3. So you expect those 2 protons maybe 3 something ppm, okay? And those CH3 protons will be maybe around the 1. Okay, I'm not just the exact value, maybe around the 1, but a little bit more, it's okay. Okay, yes?
If we move the BR to the other side, is that not possible?
You can't. Because BR only can connect to CH2. We cannot connect to CH3.
There's no way that the 3 protons.
Because so this structure, after bromide, you can't. The BR must connect to CH2. It cannot connect to CH3. So this one should be around something 3 something. This 1 something ppm. Okay, and this peak area, if make it say 2, this one going to be 3 because for more point get bigger peak. So that's so far about the in terms number of peaks, chemical shift value, and the area. So you see the blue one is about 3 something, and the pink one is a 1 point something. Okay, because the chemical shift value, electronic effect of bromine, and the blue one, if it's 2. The pink one will be 3. So that's should be. I hope everyone here should be rock solid about these two, the aspects to this point. Okay. Then if you look at the zoom in for the pink peak, okay, you will see it's a triplet. Okay. So this one is triplet. What does that mean? Means that those pink peaks come from metal protons. Those metal protons, they have 3 minus 1, 2 vicinal protons. So when you see this is triplet, means the protons give this peak. They are metal protons because we know the area is 3. Okay, metal protons, they have 2 vicinal protons. What are the 2 vicinal protons? Obviously, the 2 CH2, the CH2 here. Okay. Similarly, if you look at those zooming this blue or cyan, the peak, you will see there's 4 lines. So what does the 4 lines mean? Means that those protons that produce this 3.4 ppm peak, they have 4 minus 1, 3 vicinal protons. So what we can see here, these blue protons, right, that produce this signal, they have 3 vicinal protons. Okay, those methods, they are vicinal protons. Okay. Now next example, look at the isopropyl chloride. Okay, again, first thing, let's look at how many peaks, how many signals you're expecting from this compound. Basically, to answer this, you need to know how many kinds of protons we have here. A tendency? Who has a tendency? Thank you. You wonder? How many signals you expecting? 3? Okay, so what are the 3 words? Obviously, if you say 3, you mean these 2 are different, right? Do you expect these 2 different? Yes. Well, do a replacement test. Okay, if you replace one of hydrogen here, put with something say fluorine, okay, because we don't have fluorine in the molecule, then replace the hydrogen here again with a fluorine. You will see they are the same compound. Okay. So but at least nothing actually. To be honest, they are not the exactly same compound. Okay, but they have exactly the same chemical shift value because of those protons. Strictly speaking, they probably are enantiotopic protons. Basically, those 2 protons here, proton here, and the proton here. If you do replacement test, you're going to generate a pair of enantiomers. Okay? But they have same chemical shift value. Okay? So you will not be able to resolve them. So you only see 2 peaks here. Okay? Only 2 peaks. Then the 2 peaks, the area ratio should be 1 versus 6. Okay, so this is things we have seen: number of peaks and area ratios, and the chemical shift value. So the smaller peak should have a higher or lower chemical shift value. The smaller peak is only 1, right? Size. Higher or lower chemical shift value than the bigger peak. Very good. Higher and much higher. Okay? Because of those 6 protons, they are further away from the electron withdrawing chlorine. Okay? So that is the rough shape you will be looking at. Okay. So the blue proton, smaller peak, much higher chemical shift value, 4 point something, and the bigger peak is 1.5 something. Okay. Now let's look at the spin splitting pattern. If you zoom in the 1.5 ppm peak, you will see it's a doublet. Okay. What does it say? What you can read from this fact is a doublet. That means the protons that produce this peak, they are methyl protons, 6 of them. Those protons only have 2 minus 1 equal to 1 vicinal proton, only 1. So in this case, obviously, those 6 methyl protons have only 1 blue proton as a vicinal proton. Okay, so that's what you read from the the spin splitting pattern. Okay, and for the blue signal, if you zoom in, you actually can find out it's totally there are 7 lines. 7 lines. Why? Let's say you count it, there will be 7 lines. So what you can say from the fact that it has 7 lines, just say, oh, these blue protons, they have 7 minus 1, 6 vicinal protons. So what are those 6 vicinal protons? It's basically this one gives the blue signal at the 4 point something ppm, and though they have 6 pink protons, they are vicinal to the blue proton. 6 of them, 6 plus 1, 7 lines. And in some cases, you may have a relatively complicated spin splitting patterns. I will not really, I will not try to intentionally test this, okay? But you need to know this, because you might see this in the sample problem. Look at this compound, okay? And let's focusing on the vinyl protons. The protons connect to the carbon-carbon double bond, not inside the ring, just the outside the ring. Okay, so basically those 3 protons. First thing is, let's make clear these 2 protons. Okay, these 2 protons, they are chemically not equivalent. Okay, they are not chemically equivalent. Let me repeat again. These 2 protons, they are not chemically equivalent. Okay. Why? Just if you do replacement test, you will see it immediately. Okay. So where did I put? Oh. So you have these 2 protons. Okay. Let's make a copy. Okay. So if you replace this proton with a random, a group you don't really already have here, let's say, make it a fluorine. You get this compound, okay? You can replace this proton, say with So I hope you know that this guy, okay, and this guy, these two guys, they are diastereomers of each other. They are not the same compound. So basically, the guy in the red frame has a E double bond, and the guy in the blue frame has a Z double bond. Okay? So these are a pair of stereoisomers. Okay? They are not the same compound. That means the two protons in question, they are not chemically equivalent. Okay? So that's important. So now if you look at if you look at this proton signal, okay, HA, actually it's split into 4 lines, okay. If these two, because both those two protons, okay, both those two protons are vicinal to the HA, both of them, okay. If these two protons were chemically equivalent, okay, you expect this guy should have split into 3 lines, 2 plus 1, if these two protons were chemical equivalent. Okay? But because the two protons are not chemically equivalent, so those two protons, they couple with those HA individually. Okay, so what you can say is, okay, so this proton, okay, split HA signal into 2 lines. Okay, and then each of those lines will be split by this proton into 2 lines. So total lines is you apply the n+1 rule twice. So this one, 1 plus 1, so this one split into 2 lines. Each one of them will be split by this one into 2 lines. So total is 1 times 1. Basically you have to do this. The total lines is basically, let's say if this one is HA, okay, here, this is HA. So the total line up, because these two guys are not, they're different. Say this one and these are different. Okay, so total multiplicity of this signal, okay, is 1 plus 1. That's the impact of this proton with HA, okay, then multiply by the impact of this proton with HA, 1 plus 1, okay, equal to 4 lines, okay. So that's how the complicated spin splitting works. And similarly, I'm going to give another example, say CH3, okay, and the CH2 and CH2 Br, okay. So for this compound, okay, first, how many signals you're expecting from this compound? Yes, 2. Okay. Basically, we'll look at what you told me that's 2 signals. Okay. So you're thinking basically CH3 is one signal, and those 2 CH2s have the same. So the key point is, I think you're all clear. CH3, CH2 are different, right? So now you try to replace one CH2 here. Let's say with fluorine, you'll get a CH3, CH, F, CH2Br. Okay, this is one compound. Okay, then if we replace one CH2 here, one proton here, next to bromine, CH3, CH2, CH, fluorine, Br. Do you think this guy is the same compound? If they're not, means the CH2 are different. Okay, the 2 CH2 different. So you could expect 3 lines here. Okay, 3 signals. the three lines, three signals. And the chemical shift value should be this one probably 3 point something ppm. This one may be close to 2. This one is close to 1 ppm. 3 signals, okay? And I hopefully should, how many lines this one will be split into the CH3 protons? How many lines? Count number of vicinal protons. How many? Only vicinal proton means proton on neighboring carbon. How many you have here? How many? Please count. How many vicinal protons the CH3 protons have? Please louder. 4. Vicinal means the proton on the neighboring carbon, just neighboring carbon. Only 2. Okay. So this one, 2 plus 1, the signal of CH3 proton should split to a triplet. Okay. 3 lines. Okay. Let's say I'm not going to term 3 lines. Okay. The signal 3 lines. Okay. And the blue one, how many lines should be split into? The CH2s, the CH2 next to bromine. This one, again, count number of chemical equivalent of vicinal protons. How many of the blue CH2s they have? Vicinal. Again, the proton on neighboring carbon, exact neighbor, just immediate neighbor. Let's say, if you sit here, these 2 students are your immediate neighbor, okay? You don't care about the person here, okay? Because there's no chemical bonding, okay? So only counting, the protons on the immediate neighbor, okay? Like if you look at blue ones, okay, only immediate neighboring carbon is green one. And how many protons only? 2. So this one also is a 2 plus 1, 3 lines, okay? Now the middle green CH2, how many vicinal protons they have? 5. Okay, but the problem here, the 5 vicinal protons, they are not equivalent among themselves. The 3 of them is the methyl one, obviously the other 2 are methylene one. So they must interact, must couple with the green proton separately. So how many lines this one can split into is a very complicated situation. It could be up to, the 3 methyl protons gonna split into 3 plus 1, okay? And the 2 blue protons gonna split into 2 plus 1. So this signal, they could split into up to 12 lines. But whether you're going to see all 12 lines depends on your situation, okay? It could up to 12 lines, could, okay? Just to say, this very complicated situation, okay? It could, okay? So you don't need to worry about that. If you see very complicated splitting pattern, you don't need to really look into that. You can, you don't have to use that information. Just use the purpose of the conformation. But if you see clearly 3 lines, doublet, singlet, those are very useful. So if you see a signal clear singlet, means that the proton give you that signal have 0 vicinal proton. Okay? If it's a doublet, it's 1 vicinal proton. Triplet, 2 vicinal proton. If the complicated one, forget about it. We don't use that information. Okay? Just well defined, the singlet, doublet, triplet, or at most quartet, you can make use of. Complicated one, don't use it. Okay? Just say, complicated spin-splitting pattern may exist. And the other thing is just we have seen that in asymptotic protons means the replacement of the proton in question can generate a pair enantiomers. I think the example we have seen here, okay? And the enantiotopic protons, they have the same chemical shift value. Like those two protons, they are enantiotopic protons, okay? Because replace, these pair of protons with the general pair of enantiomers. Enantiotopic protons, they have the same chemical shift value. And also if the two protons have the same chemical shift values, they will not split, the signal of each other because they have the same, same position, so no splitting. Okay? So but if the replacement of the two protons gonna generate, a pair of diastereomers, and we know that those protons are not chemically equivalent, like the examples we have seen show here. I showed you here. Those two protons, okay, if you they are replace these protons with a test group, gonna generate one compound, okay. Replace this proton with a test group, generate another compound. Those two compounds, they are diastereomers. So we say these two protons are what's the name called? Diastereotopic protons. Diastereotopic protons, they have a different chemical shift value. But the chemical shift value, but often they are not too far away from each other. An example you can see here, in addition to the two vinyl protons, we also could have a situation that the two protons connect to the same carbon. This kind of two protons we call geminal protons. Two protons on the same carbon, and this carbon is next to a chirality center. So the carbon 2 here is a chirality center. So in this case, these two HA and HB, they also are considered as diastereotopic protons. So because if you think about replace this one with D, you get this compound. And then if you replace this one with D, you're gonna generate this compound. And those two compounds, they are a pair of diastereomers because you have a well-defined chemical shift value here. This, let's say, the what is chemical, what is the configuration here. So this one is this is the lowest, this one is the highest. So if we rotate it, probably this one is a S, configuration. So this one is S, this one is also S, but if you look at this chirality center, then this carbon 1 and carbon 2, if you look at its configuration, one will be S, the other will be R. So these two guys, they are pair of diastereomers, okay? So that means these two chemical shift values, they will be different. So because these two chemical shift values are different, so they actually can split the signal of each other. So if you look at the proton NMR chemical of these two protons, okay, they actually give you two lines. Basically, this two is one proton. This two is another proton. Both is splitting to the doublet. So these two guys, they are split. HA split signal of HB into doublet. HB is splitting HA into doublet because of the HA only has a single vicinal proton. This is HB. Same thing for HB, only has a single vicinal proton, HA. So if assume this is HA, this is signal of HB, both are doublet. Now let's look at a proton NMR of the alcohols. So all the alcohols, have OH group. So the hydroxy, alcohol obviously features a hydroxy group. And in theory, the hydroxy proton OH should split adjacent, the protons into a doublet. For instance, if you look at the benzylic alcohol, the name, it's not hugely important, you will see that the CH2 protons give you a peak around the 4.5 ppm, and the OH proton in this particular case give you a peak at 2.9 ppm. And you can see that the blue protons actually is doublet because of OH proton can couple with CH2 proton. And the blue protons has a vicinal proton. This vicinal is not the proton connect neighboring carbon, it's neighboring oxygen. Okay? And this one can lead to spin-spin coupling. And for the same reason, OH proton, okay, is split by two vicinal CH2 proton into triplet. This could be observed, but more often than but often this OH proton, you don't see splitting. This is because of as we know from the organic one, OH protons, they are somewhat acidic. So alcohol, OH can lose its proton. And so the OH protons can exchange rapidly, especially when the alcohol concentration is high, or the temperature is a bit high, or in the presence of acid base. So when exchange is rapid, the OH peak is not split by adjacent proton and does not split adjacent proton itself. So on those circumstances, the peak could appear very broad and can vary considerably in chemical shift value and depend on the alcohol concentration. So that's a reason why OH proton, we don't use chemical shift value to identify OH proton. So OH proton often this is last proton left. We consider, that is OH proton. But there's one easy way to for us to, it's highly reliable. It's not 100.0% reliable, it's 99% reliable. Way to, there's a very reliable way to identify OH proton is if you add D2O, D is deuterium, H2. If you add a D2O, into alcohol, and we know water or D2O has a the heavy version. D2O have the two OD groups, and OD groups chemically they are very similar with OH group. That's isotope. Okay? So chemical behavior are very similar, so they can undergo chemical exchange with alcohols. So this exchange can convert OH group in the alcohol into OD group. Now, the interesting is because we are the instrument, when we collect the proton NMR, the instrument is tuned to detect proton H1. Okay? So under those conditions, you will not be able to see the D. So if you think alcohol, a peak maybe come from the OH group, you can put a drop of D2O, then shake it, okay, for a minute or two, then put it back. If that peak disappears or becomes so much weaker, and you know that peak is OH group. So like here, okay, if you suspect, okay, I'm not sure the blue peak or this peak is OH group, then put drop of D2O and shake it, okay. If this peak is gone, okay, and then you know, this is the OH group, okay. If this peak is gone, then this one is OH group. So this is a very reliable way, although it's not 100% guaranteed because you could have some other protons also can participate in exchange reaction. It could, okay, but usually it's pretty reliable.